Hello again, it's Dave Giles here for the next lesson of Cambridge International Education, IGCSE Physics, Unit P3 Waves. Today we are looking at lenses. So the bulk of the lesson will be describing how images are formed using lenses, and we'll also describe how magnifying glass and glasses work. So some key terms, this is a recap of what we talked about previously. A real image is one which can be projected onto a screen. A virtual image can't be projected onto a screen. And previously, we looked at using ray diagrams for things like reflection. So here, the word cat, we have the image. So we have, just draw two lines, one at the start of the word or the object, one at the end of the word or object. And angle of incidence equals angle of reflection. And you extend the line backwards to get where the image appears. And we get an image which is laterally inverted, same size as the object, and it is virtual. Now, it's a reminder that virtual just means that it can't be projected onto a screen. So, another key term, which should be new to you, is convex and concave, two different kinds of lenses. Technically, these are double convex and double concave lenses, but you only ever look at these at IGCSE. So another word for a convex lens is a converging lens. And I think the specification generally uses the word converging, and concave, it uses the word diverging. Now, personally, I tend to use concave and convex. And one of the main reasons is just because when I was younger, that's the terms I was taught, rather than diverging and converging. So the way I remember a concave lens is it's a little bit like a cave. It goes inwards. So if you remember a cave, you go into a cave, concave goes inwards, and the other one is convex here. No real way to remember it, but it's the one that is the opposite to concave. Okay, moving on. So this here is a ray diagram for an image formed using a convex lens. And this here is just one of the key terms we need to look at is the focal point. So that is where all the rays are join together, the focus at this point here. This is the focal point, and the distance from the center of the lens to the focal point is called the focal length. So this is the term we'll be using quite a lot, these two, focal point and focal length. So when we draw a ray diagram for a convex lens, we can use the ray diagram to predict the type of image different convex lenses will produce, because you get different ones for depending on where the image is or where the object is. The image will form at the focal point of the convergence of two light rays, which originate from a single point on the object. So here, I've got my gummy bear man, and I've got a lens here. This, like I say, this is not going inwards like a concave, so this is a convex lens. And you do one ray just going from the top of the object through to the center of the lens, like this. Then you do another one going from the top of the object straight ahead to the center of the lens, and then down towards the focal point here. And where these two points meet is where the image will be formed. So the thicker the lens, the closer the focal point will be to the lens as well. That's a little something to add for your knowledge. So now we're going to look at the different kinds of images that we get. So depending on where the object is, you will get a different image. So this is for a convex lens. So we start quite a distance away. You can say it's getting bigger and bigger as we get closer until we reach the focal point. Then it actually appears to be on this side of the lens, the object. See the size of it's continually changing. And now as we go from the focal point to the image, to the lens, sorry, it then starts to get smaller. See now it's getting smaller, and then we'll go past 2 times the focal point length. Again, it's getting smaller and smaller now. So let's actually have a look at what kind of image we're getting at different points. Two seconds. So here, if the image is beyond 2 times the focal length, the image, it's real, inverted, and reduced. So that means by reducing, it's made it smaller than the original image. If we put it on exactly 2 focal length, the image forms a 2f on this side. It's real, inverted, and the same size. And now, between the focal length and 2 times the focal length, the image formed beyond 2f on this side. It is real, inverted, and it is also enlarged. Then, if we put it on the focal point, the image forms at infinity. So these rays here will never cross because they were parallel to each other. So you don't actually get an image formed if it's on exactly the focal point. Okay, and then as we then go between the focal point and the lens, the image is virtual, the white ray up, and it is enlarged. Okay. And it is on this side of the lens. And one thing to point out is if it's on this side of the lens, then it is virtual. If it is on this side of the lens, then it is a real image. Okay, so I'm going to show you how to draw a ray diagram just for this arrow. And if you want, you might find it useful to screenshot this and then try and draw it yourself if possible. 1 second. Okay, so first line is from the top of the, so I have a little computer freeze up here. 1 second. Okay, I'll fix the little freeze up there. So the first ray goes from the top of the object to the center of the lens, and then down through the focal point. The second ray goes from the top of the object through the center of the lens, and then the object will appear where the two lines meet. So if you've drawn it out, you should have it roughly in the middle, sorry, of this box here on the right. And you can see it's going to be bigger than the original image. Now, if we were to use a concave lens instead, then these questions come apparently appear less frequent on exams. However, it's worth covering just in case. To find the focal length for concave lens, rays parallel to the principal axis must be directed through it. As the rays diverge, we must trace their path backwards to find the point where they cross over. So this here is the focal point, while the distance from the focal point to the center of the lens is the focal length, just like with a convex lens like we looked at previously. So again, let's have a look at the object formed. Pardon me. You can see now it's never bigger than the original object, so it's never magnified. So if I just skip ahead, you can see here the image always has the same qualities. It's always on the left, so therefore it would be virtual. So it's on the same side, well, by left side, I should say the same side as the object. So it's virtual, not inverted, and reduced. It is never enlarged by a convex lens. Sorry, concave lens, sorry, my mistake. So To draw the rear diagram for it, again, you can take a screenshot of this, but this time, draw a line to the center of the lens. Then from the focal point where these meet, and on this side, from the top of the object through the center of the lens, where the two lines cross over, that is where we get our object. And you can see here it's diminished, it's not as big as the original object. So, quick exam question. State one word to describe the nature of the image in figure 3. So this is a concave lens, just to point that out. So it's upright, virtual, and diminished. And calculate the magnification. Now, magnification is just the image height divided by the object height. So it says 1 centimeter here, the object height is 4 centimeters, so it's basically a quarter or 0.25 the magnification. So another exam paper question here. So you'd rule a complete rear diagram to show how an image of the object is formed. And you can see here that this here is a convex lens. So we do one going straight through the middle. Now, even though the lens isn't very tall, you still go to the center of it, but above the lens. So here, and then down through the focal point, and this is where the two meet. So you should have it about 2.6 boxes approximately to the right of the lens. Describe the nature of this image relative to the object. So you can see it is on the right side, so the opposite side of the object. So it's real, it's bigger, so therefore it's magnified, and it's inverted. And this here is just a quick summary of everything we've said about convex and convex and concave lenses here. It's just, like I say, if it's beyond 2 times the focal point, it's real, inverted, and reduced. If it's between f and 2f, the image forms beyond 2f, it is real, inverted, and enlarged. If it's at the focal point, then you don't actually get an image because the lines are parallel. And if it's between f and the lens, the image is virtual, the right way up and enlarged, whereas with a concave or diverging lens, the image formed is always virtual, not inverted, and reduced. Have a quick look at some paper 2 questions on this. The rear diagram shows the formation of an object by 2 different converging lenses. Which row describes the image produced? In diagram 1, so you can see the image is on the same side as the original object, so therefore it's virtual. On this side, it's the opposite side, so therefore it's real. So the answer is C for this one. Okay, for the next image here, which arrow shows the direction which the ray is as it leaving the lens. So as it leaves the lens, it will go through the focal point. So it will be there. So a thin converging lens is used to produce a real image of an object. Which statement about the real image is always correct? It's the opposite side of the lens of the object. And a student passes parallel rays of light through 4 different converging lenses. He measures the distances x and the distance y for each experiment. Which lens has the longest focal length? Well, the focal length is distance from the center of the object to where the rays form. So here. So it's one of the biggest y. So that would be this one here, 3.1 centimeters. A thin converging lens in a camera produce a real image on a photosensitive surface as shown, at which position is the image of the top of the object formed. So the top of the object will go through here, down there, so the answer will be C. Okay, so that's the first learning objective complete. Describe how images are formed using lenses. The second learning objective is describing how magnifying glass and glasses work. So we'll look at the magnifying glass first, pardon me. And this here is a typical magnifying glass. This one looks more like a children's toy version of one. And you can see, if you look at the side here, that it's a convex lens. Okay, so the way it works is basically the exact same as a convex lens. So you can see here, if you want it to be magnified, you need to have your eye at a certain place. You can see here it's between F and 2F in this example here. And the image as well, so it needs to be in the correct place. So quick questions here. A magnifying glass is a converging lens used to make an object appear much larger than it actually is. That is, the image has to be magnified. This works when the object is placed at a distance less than the focal length of the lens. Okay, so that is magnifying glasses. And the next thing to look at is eyeglasses, as some people say, or just glasses, as most people say. So you've got two kinds of incorrect vision. The first one is nearsighted. So nearsighted people can only see objects which are close up clearly, and they need corrective glasses or perhaps contact lenses, both do the same job to correct their vision. Whereas a far-sighted person can only see objects clearly, which are quite a distance away. Now, what you've got to remember is whether you're talking about nearsighted or farsighted, we're talking about the thing which the person can do normally. So they can see normal farsighted if someone's farsighted, or they can see something close up easily if they are nearsighted. So with a short-sighted person, I mean, the light from the distance focuses short of the retina. Okay, so it's focusing too close when it's at a distance. So you use a concave lens to correct that and get the focus correctly in the right place. Whereas if a person is long-sighted, light from the source focuses past the retina, so it's focusing here because you want it focused on the retina. So you use a convex lens to correctly focus it. Okay. So quick exam question. A converging lens is being used as a magnifying glass. Which statement is correct? And it's the image is further away from the lens than the object is. And here is a Paper 4 exam question. The truck, so this is part of an exam question, so we talked about a truck driver earlier, wears spectacles to correct long-sightedness. Figure 5.3 shows how a blurred image of an object O forms on the retina. Any effect of the cornea on the ray of light can be ignored. On figure 5.4 show how long-sightedness is corrected by adding a suitable lens in front of the eye, continuing the path of the three rays of light until they meet to form an image. Okay, so this person is long-sighted, so we correct that with a certain type of lens. So you can see here the kind of lens we're going to correct it with is a convex lens. That will then bring the image, sorry, the lines slightly this way. This one that's going straight won't change. And then the cornea here, sorry, the lens that's in the eye will then sort of focus it again, sort of change direction here, the rays, and it'll change direction here, and now the image is formed in the correct place. Okay, so that's the second learning objective, describe how magnifying glass and glasses work. The next lesson will be on dispersion, which I'll be uploading very, very soon to YouTube. Thank you very much, everyone, and I shall see you in the next video.